I don't know if you hear me. Maybe now you hear me. Did
Yes,
you?
yes.
Oh,
I was
great.
LeFloch.
Great. It's always a little bit technical, but it seems to work fine.
Yes. How are you doing?
Yeah, I'm doing fine. So I'm in Paris, and there's a bit of jet time difference, but it works right. So good morning.
Bonjour.
Bonjour. So I guess it's all on Zoom, or do you have an? Is there a lecture room also, or everybody will be on Zoom?
I don't think so. This
Yeah,
semester, I don't think so. Yeah.
it's only on Zoom. Yeah, I mean sometimes it's mixed. You know, so it depends. It depends the countries now. It has become complicated.
Yeah, it's complicated. I think the speaker need to get tested before coming to campus. So everything is complicated now.
I see. I think in
but Yao is also Professor Yao, who's in China. So
okay.
We still need to be online.
Okay. Sounds good. Probably should I start sharing the screen so we see if it works well?
I just enable the screen sharing. Yeah.
Let me see. Preview. Share. Okay. I think I need to make it centered. Okay, is that fine?
Yeah.
Okay, thanks. So I can see Lydia. Good morning.
Hi everyone, salut Philippe.
Hi.
How are things in Paris?
Yeah, it's okay. I think now this is a fourth wave, but it's decreasing. So
yeah.
You know, waves of different sizes. So it's not strictly decaying, right? Otherwise, it would be somehow reassuring. But yeah, it's not so clear, right? What's going on?
Yeah, difficult.
Yeah, in the US, I saw the numbers. I mean, the numbers in the US are not very good now. Again, I think.
Not really. Yeah, so it's really a big difference between states where the people
right.
vaccinated and not. So yeah.
Right, and south. Yeah, in France it's more uniform, but not very good.
Yeah.
It's really amazing that people predicted that it will go away, and every 6 months we feel that it is over, right?
Yeah.
But,
exactly.
So you're mostly in Ann Arbor, Lydia, at this moment?
Yes, we didn't travel to Europe this summer. We went actually last winter, I have to say. But yeah, we're mostly here. We took maybe a couple of small trips, but yeah. What about you? Have you traveled?
Not at all.
That's it. Right.
I mean, not even going to the university. So I live in the suburbs of Paris. And going to the university, I need to take the train. So of course, I did that some number of times, but not every week.
Yeah, we started teaching in person 2 weeks ago. So
okay.
Hi, Philippe. How you doing? This is Jim Eisenberg. Do you hear me? I guess not.
Okay. So should I start?
That's good.
Jim was saying hi.
Okay.
Yes,
sorry,
yes.
sorry.
So let me introduce Professor LeFloch. I guess everybody here probably knows Professor LeFloch.
That's good.
Oh, hi, Jim. I only see you now. Very glad to see you, Jim.
Yeah, we're just waiting for Professor Yao. So yeah, so
okay.
She joins and then yeah.
Very nice.
Hi, Martin. Where are you situated now?
Hi, Lydia. It's good to see you. I'm in Cambridge.
Okay. Yeah.
And teaching is also in person for us now.
Oh, I see.
So I'm teaching without a mask, which is great.
Okay. Wow. Yeah.
Really? Without mask?
Yeah, there's a 14 feet rule, but yeah, I can. Yeah. So if the students if they're not too enthusiastic, it's okay.
Strange. No, we need to wear masks. We also need to get tested almost every 3 years. 3 days, sorry.
3 years.
3 days.
Yeah, for us, it's once a week.
Okay. I see.
Yeah, so we have a vaccine mandate and we have to wear masks, everybody indoors in class also.
Yeah.
So Jim, good to see you too. You moved, you said. How do you like the new place? You're muted, Jim.
Okay, I think I'm unmuted now.
Now it's, yeah.
No, the new place is very nice. It's still lots of chaos going on, but we like it a lot. It's a very pretty place. This is in Northern Virginia, just across the Potomac River from DC.
Nice.
Yeah. And I'm still trying to get a job with the NSF.
Oh yeah, right.
Many of you might find it weird, but I miss teaching. I very much miss teaching a lot.
Yeah.
All right.
Maybe.
So Professor
Okay.
Yao is here, I guess.
Yeah.
So yeah, we can start. Yeah.
Good. Thanks.
Right. So let me introduce Professor LeFloch a little bit. I guess everybody in here probably knows Professor LeFloch, but yeah, Professor LeFloch is like a global expert in like nonlinear hyperbolic PDEs and application to many physical systems, including, of course, general relativity. So one of the main work of Professor LeFloch was, there are many important works he's done, but one of the main thing which is relevant to general relativity that I'm going to mention is the hyperboloidal foliation method, and applying which he actually gave a proof of stability of the Minkowski spacetime in the presence of massive wave fields, or like the Klein-Gordon fields. So yeah, I guess I'll just now hand over to Professor LeFloch, and I'm very excited to listen to his talk. Yeah.
Thank you. Thank you very much, Pascal. It's really a great pleasure to be talking in this seminar. As the title suggests, I'm going to talk about 3 different topics, results. And the first one will be with T.K. Nguyen. He's in Paris. We have been looking at the Einstein constraint equations. We prescribe the asymptotics. We want to construct asymptotically flat manifolds. And to do that, we introduce what we call the seed-to solution method. And in this case, the geometry has quite low decay at infinity. So this is one of the issues I would like to discuss. The second result, I will talk much less about it, is this global nonlinear evolution of self-gravitating massive fields with Yue Ma. He's in Xi'an. Again, in this case, there is low decay at infinity, and we also study the time asymptotics under low decay conditions. There is no scale invariance if you have massive fields. So this is the main difference from results of stability of Minkowski space times that existed before. And the third result is this result with Bruno LeFloch and Gabriele Veneziano involving singular geometry. We look at the problem of bouncing at cosmological singularities. So there's a lot of work on starting from the singularity using Fuchsian techniques, for instance, or converging, evolving toward the singularity. But what we do here is quite different. We define a notion of bouncing to cross the singularity, as we have discovered something we call the laws of bouncing cosmology, that tells you or actually classify how you can cross a singularity in GR. So you don't need me to spend much time on the equations. Of course, we know that there is the evolution part and the constraint part, and I'm going to talk about both. There are a lot of results on stability of Minkowski space, and more recently, enormous progress on Schwarzschild and Kerr. My interests are situations where you include matter fields, or you go beyond asymptotic symmetry, or you allow singular solutions, as I just explained. So these are the three topics I want to tell you about: the nonlinear stability of Klein-Gordon fields, the constraints beyond asymptotic symmetry, and the evolution in presence of singularities and crossing singularities. So the way the talk will be presented is that I have 3 slides to begin with that will summarize the results for these 3 topics. And then I will pick up 2 of the 3 topics to give you more details and more, more theorems and ideas about the proofs. So the first topic is the construction of constraints. I put just a few names here. I mean, basically, Lichnerovich in the 60s and some other work by Corvino and Schoen much more recently. I will put more names later on in my lecture. And since this is just a 1-page presentation of this result, let me simply say that Carlotto and Schoen had a result of what they call localization at infinity. The result involve a matrix that decays. So you have the situation of a flat solutions to the Einstein constraints. And the construction, they produce a decay at infinity that was not at the harmonic level, 1/r, but it was off in some angular region. So of course, I'm going to return to that in a few minutes. But let me simply state one of the results we obtained with Nguyen. What we do is that we relax the requirement at infinity to in this localization properties that Carlotto and Schoen had imposed. And we define this problem of asymptotic localization. And again, I'm going to return to that, but there is a picture here that should give you the basic idea. You look at infinity, space-like infinity. We are actually on just a Riemannian slice of our space-time. And you want to construct an initial data set, or actually a family of initial data sets that coincide with the Euclidean metric in one angular region and coincide with the Schwarzschild metric in another angular region. And these 2 regions are connected by a narrow region And this is my result here. And again, I give you more details a little bit later on. But the results in this setup is that you have the Einstein constraints on a 3 manifold, say with one asymptotic end. You decompose infinity into, in fact, 3 regions. And what I'm able to do is I'm able to construct a solution to the Einstein constraints, which is asymptotic to the Euclidean metric modulo 1/r perturbation. But in 2 regions, in 2 specific angular regions, I call them C Euclidean and C Schwarzschild, my solution is actually asymptotic to the Euclidean metric or to the Schwarzschild metric at a higher order rate, meaning 1/rq, where q can be as close as 2 as you want. And the strategy to do that is to have first a more general result where we prescribe a seed metric at infinity. So basically you pick up more or less any behavior you want to capture at infinity. You construct a solution of the constraint based on these ansatz. And then you realize that there are quantities which we have called mass corrector that in some way spoil your solution at infinity. And then you need to design seed data that involve certain free parameters. And by adjusting these free parameters, you can actually control the behavior at infinity exactly like you want. And in my case, exactly like I want for this specific theorem, means that I want my solution to be asymptotic Euclidean or asymptotically Schwarzschild. And the connection between is precisely of the order of 1/r. I will give you more of these statements in a few minutes. Now, based on this construction of initial data set, with Yue Ma, I have studied the global evolution based on the Einstein equation. And more precisely, I'm looking at the coupling with the Klein-Gordon field, for which we know by a lot of results by physicists and people doing numerics that the dynamics is much more complex and rich than the one that you see in the vacuum. And in particular, the decay, time-like null or space-like infinity play now. So can you see the screen? I see some note on everything is fine in, yeah, okay. So there are 2 proofs of nonlinear stability for Klein-Gordon field independently. So one has been given by Alex Ionescu and Benoit Pausoder using the method of resonances. So this is a technique that was, I think, initially developed at the Courant Institute with Jalal Shatta, Pierre Germain, Nader Masmoudi. So this is a technique that they have developed much further in order to prove the stability of Minkowski space with Klein-Gordon field, and myself with Yue Ma at the same time. So we started this work back several years, and along the years got several results. And the most recent result, which will be posted soon, is a result where we pick up exactly the data that I presented in the previous slide, this initial data constructed by this C2 solution method, and we evolve this globally. And our result is parallel to the result that you know in the vacuum. So it says that you have to be close to a slice of Minkowski space. The matter field has to have sufficiently small energy. And again, the decay condition that we have at infinity can be possibly very non-symmetric. And the decay of the metric can be as close to 1/√r. I mean, not quite 1/√r, because then the mass, the ADM mass will be infinite. But this is a regime that we approach. So we cover all the regime where the ADM mass is finite. And the result says that there is the initial value problem for the Einstein equations admits a globally hyperbolic Cauchy development. We have a foliation, and the foliation can be either given by asymptotically flat hypersurfaces, which is somehow more standard in this business, especially because we use wave coordinates following the work of Lindblad and Igor Onionsky. But we also associate to our spacetime, and this is fundamental for the proof, we associate a second foliation, which consists of asymptotic hyperboloidal slices inside a wave cone region, and asymptotically Euclidean slices outside that region. And this is a technique that we developed first back in 2014 for the inside region, and then in 3 years later in this archive paper we cover the full domain with a certain decay. And so the most recent development have been to weaken the decay conditions at infinity and cover exactly what you expect to assume finite ADM mass at infinity. So otherwise, we use the symmetry of Minkowski spacetime like it's customary done, except that we are not allowed to use a scaling field because it would not commute with the Klein-Gordon operator. So this is a major difference with all previous work, and Ionescu Posoder had to also face the same difficulty. And in our case, we have to derive a certain hierarchy between the equation, distinguish between the contribution, the nonlinear contribution from the geometry, from the matter, and analyze these interactions using sharp energy or sharp pointwise estimates, which we deduced by first establishing functional inequalities of Sobolev, Hardy, and Poincaré type. But these inequalities are stated and proven on our Euclidean-Hyperboloidal foliation. And to finish this screen, I want to recall to everybody that Daniel Tataru he's probably the first who really investigated the idea of using hyperboloidal foliations. So this was back, I don't know, 10, maybe 15 years ago even, to analyze nonlinear wave equations. And on the other hand, after our work on using this hyperboloidal foliation, there have been work on Vlasov matter and even using also these techniques for the analysis of some compactification of Minkowski space. I mean, Minkowski space plus some compact dimensions. So the third topic, so I'm still in the list of summarizing what we have been doing. So the third result concerns bouncing at gravitational singularities. And for me, this is a quite exciting topic, which I learned from Gabriele Veneziano. So he's a string theory researcher, and I learned a lot from him. So bouncing cosmology, so this means that in your space-time, there is a singularity hypersurface, and you don't content to approach this surface or to leave this surface, you would like to cross this surface. So you should think of a geometry that is contracting, then again expanding, and the question you ask is what sort of junction you can put to go from one side to the other. And this is to be, will be understood by doing suitable asymptotics near the singularity. The singularity can be quite complex. So again, like for the massive field, it can become very complicated. So you have to put yourself in a situation where you control some of what's going on. So what we treat is a so-called quiescent regime or monotone regime. And we define suitable rescaling of the metric and the second fundamental form and the matter field. I'm going to explain what it is in just 2 minutes. But in short, the short story is that you have this data on one side of the singularity with a minus subscript, the same data on the other side in the future with a plus, and you want a map that jump from one set to the other set of data. So these are functions, if you like, or it's a singularity data set on your singularity hypersurface. And what we have done, so again with Bruno, LeFloch, and Gabriele Veneziano, is to discover certain laws that allows you to do this junction. So we are not looking to tell you that this is a specific junction that you should use. What we are asking is to describe all possible junctions that physicists could discover or could propose. So we look for a classification and certain laws, and we have found 3 laws related to the scaling of the Kästner exponents, another law that we call canonical transformation of the matter, and the third one, directional metric scaling. I'm going to explain what it is. So all this work is done by analyzing an asymptotic version of Einstein's constraints. All previous works were done by physicists, in fact, in this problem. And they always work with symmetric spacetimes and typically propose spatial junctions. So that's not our point of view. And our point of view leads us to distinguish between universal scattering laws that every junction has to satisfy to be consistent with the Einstein equations, and model-dependent scattering laws. And these laws are somehow part of the 3 laws I just stated. So they contain this idea that part of the information is universal and part of the information is model dependent. And I'm going to give you formulas to explain that. Okay, so if there are no questions, I propose to start so one of the 2 topics I would like to emphasize now, scattering maps and cyclic spacetimes. So I guess I already explained this problem of bouncing. If you think of junctions, you immediately think of work by Israel in the 50s or 60s, but his work only concerned regularity hypersurfaces. So meaning that on both sides of this hypersurface, the metric and the second fundamental form are just smooth, and they have certain limits. Maybe the limits are discontinuous, but limits exist. So this is not our case. In our case, we are more making connection with Belinsky, Kalashnikov, Lifshitz work, and they understood in the 60s that again there is a very rich and complex dynamics, and asymptotics near singularity hypersurface has to be done carefully to understand the dynamics. And what we are doing here is we put ourselves in this monotone regime that has been studied probably first mathematically by Alan Rendell and Lars Anderson, and then a number of work have been done in this sort of direction, Fuchsian or otherwise. So I put a few names. Of course, Jim Eisenberg also has been interested in this issue. So the lists are very partial here. And then what we do is that we are going to define scaling quantities. Okay, so rescale metric and second fundamental form, and define a map that define a certain scattering from one side to the other side. Having that, so if I give you such a map, I can introduce a notion of cyclic spacetime, and we specify S cyclic spacetime to explain that there is no canonical way to decide how the bouncing should be done. The bouncing will be done according to a certain rule, and the question is what rule you are allowed to impose, and can you classify these rules? So that's what we do. We work with general spacetimes. There is no symmetry or special junctions assumed. We rely on the constraints, and we discover these differences between universal aspects of the laws and model-dependent aspects. So to formulate the problem, we introduce a foliation, Gaussian foliation in the vicinity of the hypersurface, singularity hypersurface, and we express the Einstein equations in the standard ADM form. So G will be a function of tau and will be the induced metric, Riemannian metric on a slice. The intrinsic curvature, extrinsic curvature, sorry, is denoted by capital K. And there is a matter tensor, which we will describe by a scalar field. So the scalar field is taken to be massless in this presentation, but a massive field won't change basically anything to the analysis and the conclusions. So I put a few more names for people who have studied the Einstein flow for a more geometric point of view, starting with Mike Anderson. I think he was the first person to really push this idea, and Vince Moncrief also had some even earlier work. And so the way we view our problem is to say that there is an Einstein flow before this singularity hypersurface. There is a flow after in the future of the singularity. And the question, so we are not looking at any fancy big problem. We look at a specific question, is how we can connect data before and after the singularity. Okay, so we have G, K, phi 0, phi 1 minus, and the same quantities with a plus. What rules I can put? So of course, to answer this question, you need to have an information about the asymptotics. So this is what I discussed first. I wrote the formula for Kastner profiles that probably most of you would know. And in this ansatz, you think of the exponent pj to be non-constant, right? They are functions that are defined on the singularity hypersurface. So this is a good way to produce an ansatz. So it's not an exact solution of the Einstein equation, but it describes the asymptotic behavior. It's actually an exact solution if the pj are constant. But this is just a very special situation that we are not directly concerned with. And then the Fuchsian techniques, which has been developed by Alan Rendall and many people, so especially including in this audience, Jim. So the construction scheme that, again, many people have been developing is to put data on the singularity and evolve. And with this idea that the Einstein equations can be essentially reduced to an ODE system in the vicinity of the singularity. So the notion behind is called the velocity-dominated condition, or ansatz, removing all spatial dependency of the equations and decide that this is a good ansatz for your solution. And then you use Fuchsian argument to produce an actual solution. So we rely on this kind of construction, but what we do, so our contribution is to study the asymptotic data, the asymptotic constraint equations, and address the issue of the junctions. So I do that slowly by writing the asymptotic constraints. So the asymptotic constraints are formulated in the following way. G minus is a Riemannian metric. K minus is a two tensor, which we take a 1-1 tensor. The trace is 1 because we think of having a CMC foliation. So after a certain rescaling, this is a condition that we get on the extrinsic curvature, K minus. And then the Hamiltonian constraint reduces to an algebraic equation. The momentum constraints reduced to a divergence condition where the source is given by the matter field. Okay, so it's not difficult to study the asymptotic constraints. So that's not a big deal, even though you have to be a little bit careful to describe it correctly. But the point now will be to look at the set of solutions to that. So we have this notation I of H. H is my notation for the hypersurface. So if I give you such a singularity data set, you can construct the corresponding asymptotic profile. You can do that on the past and in the future. So the profile is something like I wrote below. G star of tau will be a certain power of tau, but it's tau to the power 2k minus. So k minus is our 1-1 tensor. K star is somehow simpler, just a simple rescaling of k minus. And the matter field contains a log of tau in our time foliation. Again, the regime of interest, which was studied first by Lars Anderson and Alan Rendell, K minus positive is a regime of interest for this work. So now we continue. So we define a path to future singularity scattering map on a manifold, meaning a map that takes data on I of H, produce data in the future at I of H as well. And the condition that we put on this map is that it has to be diffeomorphism covariant. So that's not surprising if you want your problem to be, your setup to be fully geometric, coordinate invariant. And so the only restriction is the second line. We impose a locality property that the restriction of our value of the map is only local. So it depends, any restriction for any open set will only depend in the future, will only depend on the past in this open set. And in a minute, I will even tell you that I impose this condition in some pointwise way. So I will repeat this condition in a minute. But for us, this seems to be a quite physically a quite natural assumption that everything will be local in terms of junction. So that's, of course, you can think of doing a global conformal transformation. And I think Roger Penrose has such a proposal. But this proposal seems to be very much consistent with the regularization that physicists have been introduced. Now, based on this map, we have the notion of S-cyclic spacetime, meaning a manifold with a Lorentzian metric and a scalar field, which has, where you can decompose the spacetime into a regularity domain, which is the outside of a singularity locus called L, denoted by L. So outside this locus, the Einstein equations are imposed. Near this locus, I'm assuming that there is a foliation, similar to the foliation I already discussed in the previous slide. And this foliation, so you have local foliation at every point of the singularity hypersurface. And I use this foliation to impose the junction condition. So I'm assuming that if I rescale my metric G and K and phi in a suitable way, I have a limit which I denote by G plus minus, etc. So this is completely in agreement with the ansatz that I wrote previously. And this ansatz was consistent with the construction of actual solutions to the Einstein equations in the vicinity of a singularity. Okay, so this condition indeed is satisfied. This limit exists near if you do such a construction. So I take these limits and I impose a junction condition on these limits. So that gives you a notion of S-cyclic spacetime. And to give you an idea, we have two results using this definition. One result is local. So locally, we can jump across a singularity hypersurface in this setup, which is really easy to formulate, to prove, to check if you have this formalism. But we also have a result which is fully global in the case of T2 symmetry. So if we have two Killing fields, we can do a global construction and construct a global cyclic spacetime according to any such map. So I will not talk more about that. So except for the local result, which I show you now, we are in the regime of quiescent preserving bouncing. So our map is also assumed to preserve this property. Of course, you can imagine a map that won't preserve this property, but that's not our point. So we do the local theory by picking up a three manifold, which is quiescent preserving. A three manifold and a scattering map, which is quiescent preserving. We pick up our singularity data in a consistent way, and we prove that there is a space-time that is S-cyclic and will be defined across the singularity hypersurface. In the case where this hypersurface is compact, we can prove that the volume of the slices is shrinking, the mean curvature blows up, and the curvature is also singular. Okay, so everything happens in the way that you could easily predict. So what is interesting for this part of the work is to formulate the setup which we have done and proposed, and then to be able to prove a global, to do a global construction in the T2 setup. But I didn't actually write this in this lecture because it takes more material. Now, let me now turn to the main topic I want to tell you for this, the classification of scattering maps. So the locality property was already introduced. And when you translate what it means that the values at any given point on the singularity, if you compare one side to the other side, they depend on local values and possibly derivatives. So this is at this stage what I have told you. But in fact, what we find of maybe more interest physically is to impose that the map is ultra-local. And you could say pointwise maybe would be another possible terminology. And so in the end of the day, we have to, we have to construct this map, and we do our classification by treating a case which is conformal map as a first example. Okay, so the main result is only assuming this pointwise condition on the scattering map. So we classify all possibilities of junctions where the junction is pointwise. So this is exactly what we do. Now, to have a little bit of terminology, a conformal map is a map that connect the metrics at possibly different times by a conformal factor. A rigidly conformal map is a map that connects the asymptotic metrics. So it's a little bit more rigid when you impose that. And then our classification, we have other cases that we study, but I'm not going to discuss more about that. But from a physical perspective, it's interesting to really, do some more fine classification of momentum preserving or momentum reversing or idempotent map or invertible map. And the last two are especially interesting if you want to include time-like hypersurfaces. And our work, which I didn't discuss this aspect here, also allows the hypersurfaces to be time-like. So the proposed strategy is to say that let's start with the constraints, look at the class of all possible solutions, analyze the class of general solutions with the asymptotic constraint without symmetry restrictions, and construct somehow suitable classes of singularity data in such a way that we can probe the scattering maps, which we don't know in the beginning of the analysis. You don't know anything about it, except that it is pointwise, in a sense I explained. And by doing enough construction of singularity data satisfying the asymptotic constraints, you realize that a lot of restrictions are immediately imposed on these scattering maps. So this is a key observations that we have made, and you discover that very few degrees of freedom are left, and you parameterize your scattering map by actually very few parameters or very few functions. The complete classification comes in two parts. First, we have the simpler class of rigidly conformal maps, which I will show you in details. And then we have also done the analysis of general junctions, but it's slightly more complicated to state. So I'm only showing you the first part, rigidly conformal singularity scattering maps. And the main result is that you have only two classes. One class which we have called isotropic rigidly conformal bands, where the metric afterwards is a conformal rescaling of the metric before. K plus is just somehow you erase some of the information. So this is the idea of this first bouncing map. You go to the singularity, you have a contraction, and when you expand, you have actually lost a part of the information. And in this case, it means that the metric G plus is a certain rescaling, lambda square. Lambda depends on the matter and determinant of K minus before. So it captures some information before. But then K plus is simply delta over 3, and phi 0 is the matter has become basically trivial, constant. Now, this is only one possibility. And the second possibility is that when you bounce, you are not isotropic, so non-isotropic. And you have slightly more involved formula where you see that K minus delta over 3 is somehow rescaled. So the trace, I should say the trace free part is rescaled by a certain factor, we call it mu. And behind this formula, there is simply one function, one real value function, which we call small f. From this small f, we construct a capital F. And from this small f, we also construct a conformal factor mu. C is a constant. So everything is explicit. So it's really amazing that starting from no restriction on the junction, you realize that there is only one function of a real variable that allows you to describe all possible junctions. Okay, so this was under some restriction of rigidly conformal, but we have, as I said, a general classification, and the result is the same. Only two classes of ultra-local space-like singularity scattering maps for self-gravitating scalar fields, isotropic bounds, non-isotropic bounds, and again we have one or two functions that describe these laws. So it's just maybe slightly more involved, but really the spirit is completely the same. And moreover, we can now summarize or represent in different ways this result. So the screen, this will be the final screen for this topic, and I guess I have some minutes left for the constraints, the usual constraints. So here what I want to say is that we can present our results in a different way by saying that we have three universal laws, and in fact they also contain model-dependent aspect. So they are universal, but in the same time they have some coefficients or some functions that come in the same time. So the first one is the scaling of Kastner exponents. So as you can see, the trace-free part is rescaled, and there is a certain gamma, which we could call a dissipation constant. So there's just one scalar quantity that tells you how you rescale the extrinsic curvature across the bounds. Then we have a second law that is called the canonical transformation of matter. So we have a conjugate matter momentum that we introduce here. And basically everything is reduced to a nonlinear map defined in this space. And this map preserves the volume form in the phase space. And it also only depends on one scalar invariant. So it's a map on this phase space, preserving the volume form and depending only on one degree of freedom, if you like, from the data before. And the third law is a little bit more complicated, but not much easier. So you connect the matrix before and after by this exponential factor involving sigma 0, sigma 1, sigma 2. So it involves a polynomial in k square. And again, we have a full description of all the degrees of freedom. Okay, so if there are no questions, I would like to tell you now in the last maybe 10 minutes, or do you have 10 more minutes?
Yes.
Okay, thank you. So now the other topics I want to tell you about is this work with TK and Nguyen. We look at the Einstein constraints. So again, the setup is quite standard for all of you. So our notation is to use the curl H for the operator, the Hamiltonian operator, and curl M for the momentum operator. In earlier work are given here using the conformal method. So this is a method that has been mostly used, and a variational method that's been developed by a number of people. Carlotto, Schoen, I think Maxwell also has worked on that. And this is a technique that we have developed in this work. So So the motivation for this seed-to solution method is to construct general asymptotically flat solutions. Okay, and again, as I mentioned before, my motivation was to get the input for the global evolution of Minkowski space. So the nature of the asymptotic decay, and basically you think of the decay to be arbitrary in some sense, right? So the technique would be to you do some ansatz, a seed data, which is not difficult to construct. So it's something that we present the asymptotic behavior. It's an approximate solution to the Einstein constraints. And then depending on certain decay parameters, we have a classification into tame data or strongly tame data. And we talk about weakest decay or strongest decay, depending on how the behavior is at infinity. So we have also a certain classification here, and we derive existent results. And another motivation was to revisit some of the work by Carlotto and Schoen on the localization problem and go beyond spherical symmetry. So having very low decay requires to be careful about the the estimates, the elliptic estimates that you have to do here, and we derive critical estimates at the harmonic level of decay, and we got this discover this idea of mass correctors. So hopefully I can tell you that now in a few minutes. So I put again the picture to remind you that this is what we have in mind. So one asymptotic direction will be prescribed, could be prescribed, another asymptotic direction is prescribed. We want to connect two things. So this is what we construct, and so let me move forward about that. So given a seed data set, so I'm not exactly telling you what I mean, but a seed data set mean a metric and a two tensor that are asymptotically flat and satisfy the Einstein equation in some approximate way. And by that, I mean the conditions that are behind, so below. So G1 is a G Euclidean plus a certain power of R. H1 is a certain power of R plus 1 with a plus 1 exponent, but we actually look at more variety of exponents also. And then you want to compare the exponent that you have for the metric to express that it is asymptotically flat, and another exponent that comes in expressing that the Einstein constraints are satisfied at infinity. So there is a second exponent I introduced here, which is called PM. M stands for matter. And it's PM plus 2 as an exponent for both, and everything has been somehow rescaled in a way so you can read on this easily the behavior of Schwarzschild. So Schwarzschild will be always my exponent P equal to 1. Okay, but my results cover the regime where these exponents P go from 1/2 to 1 or beyond 1 for some of the statements. So here, given any such seed data, I construct a solution. And then we have three cases. Either the matter exponent is small, less than 1, meaning that your approximate solution is not very good. It's not a very good solution of the Einstein constraint. Then I cannot produce somehow, I produce a good agreement between my actual solution and a prescribed solution, which is what I wrote here. Now, if you are interested in data that are of better quality somehow, where P matter is 1 at the level of Schwarzschild, then what we do is that we construct a solution which is asymptotic to G1 H1 with some error, which is higher than 1/r, 1/r, 1/r squared. So this is consistent with the discussion we have now. But there is one spurious term called denoted by M tilde over R, which we call this mass corrector. And we can tell you how big is this mass corrector in some sense. So it's given by the integral of the Hamiltonian. And the Hamiltonian was, of course, was 0 if it was a solution, but otherwise it was small, and you compute this integral and you get an idea of the size of this spurious mass corrector. So it is there, it cannot disappear in this sort of construction as it is presented. And then the decay can be better than 1 over r, or even 1 over a certain power of p, where p is large. So this is a typical result that the C2 solution method is giving you. And so I have some more comments, but probably I told you that already just by explaining the theorem, that we have regimes where we can approach 1/2 for the matter decay or for the geometric decay, or we can approach 1. You know, all these regimes are quite interesting, and they, you know, they can be discussed one by one, and we have done that. And we have even covered the case where the ADM mass is infinite. So our P geometry can be even taken to be 1/2 in our construction. So anyway, the element of proof are simply to tell you that we express the linearized Hamiltonian, the linearized momentum, the adjoint Hamiltonian, the adjoint momentum. So we have to study the ellipticity of this coupled system, play with various structure, metric, G, etc. So we play with this system a lot, do a sort of fixed point technique in weighted Sobolev and Hölder spaces. And we also rely on a framework that was introduced by Corvino and Rick Schoen a number of years ago by making an interpretation of the Einstein constraints using the Euler-Lagrange equation for a minimizer, I mean a minimization, and then writing the equations through an Euler-Lagrange formulation. So we rely on that and somehow push the techniques that they had further by going into you know, more general data, because what they have done is something that has linearized around Euclidean metric, but for us we have to do a general seed metric with a very low decay, and also study harmonic rate of decay and introduce this mass correction. Oh, okay, so I think in this lecture I won't be able to tell you more about that, but I think I have a few minutes to now do the connection with a localization problem, and maybe to say a little bit more about what Carlotto and Schoen had done. So you decompose, you look at the vacuum constraints now, you decompose asymptotic infinity into 3 asymptotic angular regions. And I guess I already explained, and we have a picture below. And so what they wanted to do, and what they did in their work, was to construct solutions that are exactly Euclidean in one angular region, exactly Schwarzschild in another angular region, and they wanted to connect these 2 regions in some way. And the result was to solve. So what they did was to solve the Einstein constraints in a narrow domain. So it was more like a boundary value, an elliptic boundary value problem that they had to formulate. And the result was that there exist such solutions, but they only could get a subcritical control of the decay within the connection between the 2 regions. So they could prove that it was 1 over r to the power p, and they can take p as close as 1 as they want. You know, there exists a solution for any p as close to 1 as you want. You will get a solution, but your solution may not have a 1 over r behavior, which is a little bit strange because both solutions, Schwarzschild, Euclidean, have this behavior. I mean, Euclidean, this is trivial, and Schwarzschild has a 1 over r behavior. So it's quite natural to want to connect these 2 metrics by also a 1 over r connection. And so they asked this problem, and we didn't answer their problem exactly, but we proposed a variant of that, somehow to relax the localization condition at infinity and require that we are asymptotic to any metric. So of course, this can be written for other choices of metrics. But the key idea was that we want now to be asymptotic at a supercritical rate. And basically any rate could be achieved. I mean, that would be a little bit more work, but And we believe that this is physically natural because there will be no way to realize that you are not exactly Euclidean or exactly Schwarzschild, but you are as asymptotic to that as fast as you want. So this is our result. Our metric is Euclidean 1 over RQ, or Schwarzschild 1 over RQ, or it is Euclidean in every direction with a 1 over R correction. And the proof of that consists of doing a further refinement of our C2 solution method. So there is a layer of additional construction, design seed data with parameters, determined implicitly, because we have somehow to fight this mass corrector that I explained. So it is there. So the only thing you can do is push this mass corrector in a narrow region between the two angular regions where you want to prescribe your metric. Okay, so this has been applied in my work with Yue Ma. Maybe I have one slide that may be too technical given the time limit, but it gives you the idea of how the construction is done. And let me conclude by saying that at this moment, I'm very excited with this problem of gravitational singularities. We believe that we have the right standpoint to uncover. We have uncovered all possible classes of junctions. We have a classification. We can cover scalar field, stiff fluid, compressible fluid, space-like, time-like, null hypersurfaces. Our construction is geometrically sound and physically sound. So we look to we have a guide to uncover the structure that is relevant, and we distinguish between universal and model-dependent structure in our presentation. We constrain the macroscopic aspects of the bounds, regardless of their origin from different microscopic corrections. So I think we have the guide to do more physics, in particular, in this direction. And so I just conclude by telling you that my interest for singular solutions go back to work I had done with Alan Randall and John Stewart a long time ago using weak conversion techniques. And so more recently with Gabriele Veneziano and a couple of papers with Bruno LeFloch now. Thank you very much for your time. Thank you.
Thanks, Professor, for the amazing talk. Yeah, if someone has question, they can unmute and ask now, yes.
Hi.
Hi.
Hi, thank you for a beautiful talk. There's so much material there. It's almost overwhelming to start listing one's questions. My first question is, can you go over a little bit the sense in which you don't solve, so to speak, the Carlotto and Schoen issue regarding the decay? I didn't quite understand that, because in the theorem you had some p's, but the p's were right, exactly. The p's were excuse me, the q's were between 1 and 2, but so I didn't quite understand that bit. And then I have another question, but that's later.
Okay. Yeah, I'm not sure what part of the result you.
So you said Carlotto Schoen have this slower decay, right? Right.
So the result, maybe I can repeat the result. So the result will be, if you look at the red equations here, they tell you that G is equal to the G Euclidean metric plus 0, nothing, in this angular region. And then they tell you that G is equal to G Schwarzschild in the second region. But in the third line, they tell you that the metric is almost 1 over R, okay? But they don't reach the 1 over R decay. So, okay, maybe that seems, just a little bit, but first of all, it requires a lot of work behind. And I think from a physics point of view, or from even a geometric point of view, it's a bit strange to not to be able to connect, metrics.
Absolutely.
So this is the point.
But okay, but then when you were saying we didn't quite solve this issue, you did in fact solve this issue.
No, because they were asking if I could put instead of big O, big O, big O, whether you can put 0, 0, big O of 1 over R. So this is their problem. This is and what I can prove any big O, so Q but this would require more work. But I'm pretty sure I can do that. So Q can be taken as big as you ask me. So instead of 0, 0, 1 over R, I can take as small as you want, and 1 over R.
I see. So that brings me to the second question, if I may, which is, you're planning to study the development problem on the basis of initial data looking like this, correct?
Yeah. The evolution. So we have done that. This has been done with Yue Ma, this global evolution.
Right. And so my question was, what happens, right? So do you get like angular resolution as to the geometry? Do you see that somehow these flat portions, right, somehow dominate most of or these large regions? And are you able to track in evolution the norms, like angular norms, where the data is larger than other directions? Are you able to get that kind of resolution?
Yeah, I mean, it's not stated in this way, but yeah. If you read the way we formulate the results, yeah, it contains this statement, because we have a whole zoo of parameters that we can choose. Yeah, we have this seed data, and then we do a perturbation, etc. So yeah, so what you say is indeed is contained in our results in a certain range of parameters. Like here, to give an idea of what I mean by parameters, I mean what I describe here, and I told you there are various parameters describing the geometry, the Einstein operators, and so you can choose these parameters as you want. You can decide that you like to have a 1 over R decay, so then I would take the GM to be 1, but maybe you want metrics that have very bad decay, so very close to 1/2, and all of that is contained in these statements. And we have in our main paper with Tika and Nguyen, for instance, I think this is what makes the paper a little bit difficult to read, is that we put various conditions on various parameters to try to cover many cases, at once. But
and the hyperboloidal foliation is used in this.
Yes. No, not
in this.
Is using, so the hyperboloidal techniques and the global evolution is using this construction as an input for the initial data set.
Right. Merci beaucoup.
Merci.
So I had a question. If your cyclic construction is that consistent with if you put a cosmological constant in there, what happens with that? Because that a cosmological constant tends to make, of course, things expand all the time.
Yeah. No, I would say I have no idea, Jim. We didn't look at that at all, and I won't be able to, to say anything reasonable in a minute. So yeah. So sorry, Jim. I really, my guess is that it's going to really change. I don't see an immediate application of these techniques to non-constant cosmological constant. Yeah, non-zero. Yeah.
Okay. Thank you. Very nice talk. Thanks.
Thank you, Jim.
Questions?
I had another question if nobody's jumping in. So this is more of a broad type question, not so technical into the statements or what have you. Could you give us some intuition and feeling as to why this hyperboloidal foliation is so useful, so powerful?
Yeah, I don't know. It's really a long story. Yeah, I mean, somehow it captures, I mean, the way I see it, if I go back to this screen, I mean, I see it as a best way to capture the time asymptotics. So you have the time asymptotics that you need to capture in your method, and the space asymptotics. And so this idea of Euclidean-Hyperboloidal foliation capture both things, and does that without any geometric. So maybe I'm not answering directly your question, but at least I can say maybe something interesting. To say that our construction using asymptotic Euclidean slices and asymptotic hyperboloidal slices is somehow a way, it's a cheap way to capture the geometry without doing the hard work that, for instance, Lydia has done to construct a fully geometric foliation. Okay.
Just so I understand the foliation, so it's asymptotically hyperbolic in the sense that in your picture, the diagonal directions in which these slopes, they're going off to infinity. That's what.
That's correct. Yes. Right. Yes.
And
yes.
Okay, and is it the case that some of the estimates are easier to do in these coordinate systems, or
no, they are not only easier, they are just they won't work otherwise. You know, typically so what we do is that we take this slicing and we compute the energy. The energy would be an energy, high order energy based on the symmetries of Minkowski spacetime, right? It's Sobolev, weighted Sobolev energy. But we do that by using the boost and using the translation rotation. I mean, there is all this geometry of Minkowski spacetimes that we use in defining the norms. And the parameter on which we do a bootstrap or bootstrap strategy is really to compute the energy along slices that combine Euclidean and hyperboloidal regions, right? And so our parameter, we call it S, and this time parameters that we introduce is fundamental in order to do the, I guess I'm not making this very clear, but it's not, you have no choice, right? This is really the only foliation that is giving you sharp bounds. You can avoid doing that if you have only a massless or vacuum case. You're in the vacuum case, massless case, then you are allowed to use a scaling field, and the scaling field is giving you much more information. But without the scaling field, you can get the good control of the energy only by this foliation.
See, and just to be clear, the trace of K is not assumed to be zero. There's no maximal assumption here on the kind of initial data that you.
No. There's no assumption.
And because you're in the Lindblad-Rodniansky type coordinates, or because
we use wave. Yeah, if you like, we use wave coordinates.
Yeah.
Right. These coordinates that Hans Lindblad and Igor Rodniansky used first to they realized that these equations were actually stable in these coordinates. So at that time, this was a surprise.
Thank you.
Thank you.
I do have one other question. In solving the constraints, were you actually using the conformal method, or I'm not sure. You didn't follow exactly what your method for solving the constraints is in your case for obtaining solutions of the constraints.
Yeah, you mean the conformal method to do a similar construction, right?
Yeah.
This probably, right? I would, I would guess so. I really don't know. I've not worked much on that, but maybe that's something we could discuss, Jim.
Okay. Okay, thank you.
So one more question. I forgive for the avalanche of questions. When I heard in passing at some point that you were right. So you're of course intimately familiar with the history of these of the papers, but the point I'm talking about is in the Corvino-Shane, it's a really kind of implicit function in theorem type argument where you end up having to kill the kernel, getting the obstruction up to the kernel, of course. But the Carlotto-Shane, of course, that doesn't happen, right? Because there is no kernel to kill, in other words. So could you describe some of the things you've talked about in this light? Is there any kernel issue that's happening? Is there anything like that?
Not in a direct way, actually, not in a direct way. So it goes through the analysis of this linearized Hamiltonian momentum, a joint. So no, the answer is no.
Okay.
Maybe one other question also, Philippe. In the case when you have your PG equal to 1/2, so you get infinite ADM mass, do you get anything interesting out there? Or you can say, well, you can extend your method to include that case as well.
We just say, first of all, we don't cover that for the evolution. Okay, so the evolution we need it to be so similar to your result. We do not cover this limit.
Right.
So we do cover the limit as far as the construction of the initial data set is concerned.
Right, and that goes through just nicely.
Yeah, exactly. It's not more difficult. It's just one limiting case that we can include in some Sobolev inequality, and that's it.
Yeah, thank you.
But it's just nice to realize that.
That's great. Thanks.
Thanks.
More questions? Okay, if not, then let's thank Professor LeFloch once more for this amazing talk.
Thank you for this invitation. Thank you.
Thank you.